So starting within our application here, first thing that we want to do is create a custom ethers provider that we'll be using to do things like retrieve the EVM balance, send transactions, etc. So we can construct this provider within custom provider and new ethers.providers.web3 provider. And as we just imported, pass in a new instance of AAWrap provider, which will create a custom 1193 account abstraction enabled provider object that we can use to drive interaction through our smart account within Ethers. So within AAWrap provider, let's pass in smart account, as well as send transaction mode.gasless, which will essentially request a gas sponsorship for every transaction that we send through custom provider. This means that if you're on a testnet, every transaction that you send will be gasless, or if you're on mainnet, it'll either sponsor it if you have enough funds in your paymaster, or it'll undergo a conditional that you set on the particle dashboard. Okay, so to close this off, let's also do any. All right, so the actual application here is going to be separated into basically 4 core components. The first will be pulling the user's address, as well as their EVM balance and BTC balance. Then we'll handle the actual wallet connection component, so allowing them to connect their wallet with the application. Then we can build out 2 functions, the first being execute TX EVM, which will send a gasless burn of a small amount of BTC through the smart account. Then we'll do a second transaction for transferring 1 Satoshi on native Bitcoin. So let's first start with the address and balance retrieval through opening a use effect. And essentially within this use effect, we want to wrap all this within a conditional that checks if accounts.length is greater than 0. By doing this, we're basically ensuring that this use effect does not get executed if the user has not already logged in. So if accounts.length is greater than 0, then we know for sure that the user has already connected their wallet and therefore signed in. Otherwise, if they haven't, then accounts.length will be 0, and therefore the logic within this use effect won't be executed. So assuming that the user has connected, we can go and define pull account info as asynchronous. And then within here, let's start by defining the address as a DDR, then await smart account .get address. Then we can set that address with set address, passing in a DDR. Now we also want to pull the EVM balance and the BTC balance. So starting with the EVM balance, let's define balance response as await custom provider .get balance and pass in a DDR. Then we can do set balance EVM with ethers.utils.format ether, passing in balance response. Now the reason we need to do format ether is because by default, balance response is going to be in a WAV format, which isn't very readable. So we're converting it to the standard ether format right here through ethers.utils. All right, now fetching the Bitcoin balance will be a little bit more complicated because we basically need to call an API and essentially dynamically generate a request based upon number 1, if we're connected to the Bitcoin mainnet or testnet, and then 2, of course, passing in our Bitcoin address through the accounts array. So let's go and do this within fetch. Then we can pass in this API right here. Now right here, we need to basically determine the user is connected to the Bitcoin mainnet or Bitcoin testnet so that we know what network to retrieve the balance on. So let's do await get network and check if the response of that is LiveNet. If it is, then we can pass in main. Otherwise, if it's not, so if it's the testnet, then we can pass in test3. So this will ensure that the URL is constructed based upon the actual network that the user is connected to. Then we can do /addrs and pass in accounts and then 0. And finally, we can do /balance. Then call .then, do the response, do r.json, then call .then on that. And pulling data, we can call set balance BTC and pass in data.balance by 28. And there we go. So essentially what we're doing here is calling the BlockCipher API based upon whether we're connected to the mainnet or testnet and setting the balance of BTC, making sure that we convert it to a standard format, similar to what we did with format ether, but of course it's manual in this case. Then we can go and call pull account info and make this use effect dependent upon the state of accounts and smart account. Okay, so now we have a mechanism for pulling the user's address as well as their balance on EVM and on BTC. So let's go and build the other 3 functions, starting with the handling of wallet connection. So wallet connection with BTC Connect is very simple. We're basically just going to be wrapping the OpenConnect modal function within a conditional that makes sure that the user is not logged in. So let's define this within handle login. And within handle login, first check if accounts.length is truthy or falsy. So within this conditional, let's go and call OpenConnect modal, and that's it. That's our entire wallet connection functionality in about 5 lines of code. So now for the latter 2 functions. Once again, this will be 2 transactions, the first being a burn of a small amount of BTC on the B-Squared network. Then the second will be a sample transaction on the Bitcoin layer 1, transferring 1 sats to myself. Let's go and define execute TX EVM, that'll be asynchronous. And to open it up, let's first go and define our signer through custom provider.get signer. We'll be using this in a moment to send the transaction, but beforehand, let's go and define our actual transaction object within TX. If you've used Ethers or Web3.js or any other standard framework before, then you're probably familiar with the structure. We're basically going to be doing the same thing as you would on any other network within any other account by simply defining things like to, and in our case, because we're doing a burn, we can set this data address right here. Then we can set the value as ethers.utils.parse ether, passing in 0.000001, as well as data as 0x. Although, of course, if you're calling a contract or anything of that nature, then you can populate data. But for now, because we're just doing a burn, we can leave that as 0x. So pretty standard. This transaction will actually automatically be converted to a user operation by our account abstraction enabled provider, and therefore can be formatted and executed through the same mechanism that you're already familiar with, and of course, directly through the smart account attached to the Bitcoin wallet. So now to actually execute this transaction, let's define TX response as await signer.send transaction and then TX. Now this will actually request the wallet to confirm the transaction, the EVM transaction. And then once they do so, it'll be pushed to the B-Squared testnet and of course settled. Although let's do one more thing, which is retrieving the transaction hash to actually display to the user, indicating that the transaction was successful. So let's define TX receipt as await response.wait and then call notification.success, setting the message as transaction successful and the description to transaction hash and then TX receipt dot transaction hash. Usually what we do here is actually embed an Explorer link into this notification pop-up, but the B-Squared Testnet Explorer is a little bit behind, so it actually wouldn't show up on the Explorer. Therefore, we're just going to go the simple route and display the transaction hash directly to the user. All right, so that's our execute TX EVM function complete. That will send a gasless burn transaction on the B-Squared testnet. Let's now do a somewhat simpler function for executing a sample transaction on the Bitcoin layer 1, of course to the account attached to the Bitcoin wallet that the user connected with. So let's do execute TX BTC. That'll again be asynchronous. Now this can basically be done in one line of code. We can define this within hash and call await send Bitcoin, then pass in accounts 0 as the recipient. Of course, you probably actually want a real recipient here, so an address that you or the user would define. But for the sake of this example, we're just going to send the Satoshi back to ourselves through passing in account 0. Then of course we can actually define the value as the second parameter, which is denominated in Satoshis. In my case, it'll just be 1. Then optionally as the third parameter, you can set the fee rate for the gas fees, but we're just going to leave it as is for now, sending 1 Satoshi back to the sender. And that's it. Upon calling that, the user will be requested to sign the transaction, then it'll be executed on chain. But let's also go ahead and throw a notification.success with once again the message as transaction successful and the description to this right here. Basically all we're doing is displaying the transaction hash, but attaching a link to it, which will take us directly to the BlockCypher Explorer, showcasing the transaction in question. And that's it. At this point, we've imported a number of base libraries, defined all of our hooks, defined some states, constructed a custom Ethers provider, pulled the user's address, EVM, and BTC balance, handled wallet connection, executed a gasless burn on the B-Squared testnet, and sent a sample transaction on the standard Bitcoin chain. So let's now go and wrap all this up through formatting everything within our JSX. Let's open up a return statement. And within these videos, what we typically do is actually skip this part because it can take quite a lot of time and be a little bit repetitive. So I'm gonna get this written and then come back to explain it. So as you can see, it's pretty simple. We're basically checking if address is defined. So just another way of checking if the user has logged in or not. If the user has not logged in, so if address is undefined, then we're displaying the connect button right here. And once the user has logged in, we can display their BTC balance on the smart account within B-Squared, as well as that smart account address. And below that, we can show them their balance in BTC on the native layer 1 chain, as well as their native BTC address. Then of course, we're presenting them with 2 buttons, execute EVM transaction and execute BTC transaction. Then one final button for logging out, which just calls the disconnect function that we defined up here. So all we have left to do now is throw in export default and then app, and then go ahead and run it and see if it works. All right, so here we are, and it looks like it worked. So let's give it a try by clicking on connect. Then I'll go ahead and select my Unisat wallet right here and click on connect. And here we go. As you can see, I'm now connected to this application using BTC Connect, which is through 2 accounts. The first is the smart account directly tied to my Bitcoin wallet, and of course is the native Bitcoin account also tied to my wallet. And we can see the balances here for both. And of course we can copy each address like this and use them later. Also, as you can see here in the top corner, I'm on the BTC testnet. If I go and switch to the live net, and as you can see that switches, as does my balance. But let's go and stick to the testnet for now, like that, and take a look at the embedded wallet modal right here. Like I mentioned, because your Unisat, OKX, or Bitget wallet doesn't have a native way to handle and manage the smart account tied to that wallet, we have the option of you including this embedded wallet interface within your application. This will allow a user the same level of functionality that they have within their main wallet, but specifically tailored to the smart account attached to that wallet. Although, of course, this is optional if you don't want to allow the user to have access to that and just want them to use your application as is, then you can set that as false. But because we set this to true, as you can see, we have our balance in BTC, even have our USDC right here, NFTs, activity, send, receive, etc. But for now, let's go ahead and close this and try our 2 test buttons. Let's start with execute EVM transaction. Of course, this transaction is being executed through the smart account on the B-Squared network, and we're signing for it natively within Unisat, authenticating it with our account. So we can go and click on sign. And as you can see, the transaction was successful with the transaction hash right here. So let's try the same thing now, but for our BTC transaction with the second button. And as you can see, the same thing here, we're signing for the transaction within the same wallet interface. Of course, with this one being on the native Bitcoin network, the first one was on the EVM chain through the smart account on B-Squared. So we can go and click on sign and pay. And here's the transaction hash right here with the link to the transaction on BlockCypher right here.